Welcome to Module 2.1.1, where we're going to talk about ideal gases. In the early days, before we really knew too much about how gases behaved, people came up with things called empirical gas laws. So the word empirical just means based on experiment, which basically means they didn't really have a very good theoretical understanding for why things worked the way they worked. They just made a bunch of observations and then drew conclusions based on these observations. So the early experiments were done to try to understand relationships between three properties of gases. Okay, and so all gases have a pressure, a volume, and a temperature. And the idea was to find some kind of relationship between these three variables, pressure, volume, and temperature. The way they did this was using the scientific method, which basically means keep one of these three variables constant and then vary one of the other ones, which is called the independent variable, and see what happens to the other one, which is called the dependent variable. Okay, so one of the first experiments that was done was Boyles Law. So Boyles Law showed the relationship between pressure and volume, keeping the temperature constant. Okay, so another word for constant temperature is isothermal. And what Boyle observed was that for any gas, as the volume changed, the pressure also changed, but it changed in a very specific way. Namely, there was an inverse relationship between pressure and volume, which means that as pressure goes up, volume goes down, and vice versa. Okay, and you can see this on the graph on the right. This is the hallmark of an inverse relationship, this kind of curved trajectory. Notice that as the volume increases on this axis, the pressure actually decreases on this axis. Okay? Or as the volume gets smaller and smaller, the pressure increases. This makes sense because if you have a gas that's in a container and you keep pushing on it, okay, as you keep pushing more and more, the pressure is going to increase more and more, but the volume is getting smaller and smaller. Okay, and so as the pressure increases, the volume decreases. Okay, so that is what's known as an inverse relationship. Next door is what we're going to call a direct relationship. Okay, this was not what was observed. Okay, it was not true that as pressure went up, volume went up, but rather the opposite. Okay, and so the point is that if you have one of these inverse relationships, you can derive an equation or an empirical observation between what happens. Okay, and so as pressure goes up and volume goes down, it turned out that the product of these two things, pressure and volume, that was equal to a constant. So another way to write that is that the initial pressure multiplied by the initial volume has to equal the final pressure multiplied by the final volume. This is known as Boyles Law. P1V1 equals P2V2. Another expression is something called Charles's Law. Okay, and so Charles's Law has a relationship between volume and temperature, assuming that pressure is constant. And another word for constant pressure is isobaric. Okay, so when Charles did his experiment, if you can imagine kind of a piston like this, okay, and the piston has the gas in it, and then there's some sort of source of heat. So this is going to make things hotter. As the temperature increased, this expanded. Okay, the piston increased in volume. Okay, and so this was a direct relationship between volume and temperature. Okay, as one went up, the other also went up. In other words, volume was proportional to temperature. So I could say that the volume over the temperature was equal to a constant. Or if I want to write this as an equation, V1 over T1 equals V2 over T2. Okay, and so this is known as Charles's Law. If you plot Charles's Law and you had a direct relationship between volume and temperature, you would expect that there would be a straight line like there would be for a direct relationship. Okay, and the straight line, if you go back to this slide, this looks like a direct relationship between volume and temperature. Okay, volume should be a constant times temperature, so I'm going to call this my constant. or I can use the letter M for slope. But the point is that if this was actually true, there should be a direct relationship, and the line should go through the origin, right? 0, 0. There's no intercept over here. Okay, but that's not what they actually observed. Okay, the experimental data did have an intercept. Okay, if you go back to this graph, you can see that the intercept is right here at about negative 273 degrees Celsius. Okay, and so this puzzles people for a while until a man named Lord Kelvin came on the scene, and Kelvin came up with a solution to the problem. Okay, Kelvin said, well, if it crosses the x-axis at negative 273.15 degrees Celsius, and I want this to be 0, I can force it to be 0. Just going to call it 0 Kelvin instead of 0 Celsius. Okay, so to go from Kelvin to Celsius, I have to take my temperature in degrees Celsius and add 273.15 to each point. Usually this gets rounded off to just 273. Okay, and so this is called the absolute temperature scale or Kelvin scale. So whenever you use Charles's law, V1 over T1 equals V2 over T2, you have to make sure that your temperature is in Kelvin, cannot be in Celsius. You will get the wrong answer. Okay. So next experiment or observation was really put forth by Galu Sack. Okay, and so Galu Sack in 1809 came up with something called Galu Sack's law. And this is really the only other combination, right? We looked at pressure and volume, that was Boyle. We looked at volume and temperature, that was Charles. And now we're going to look at pressure and temperature, which is Galu Sack. So this is at constant volume. Fancy word for this is isochoric. And once again, they observed a direct relationship between pressure and temperature, meaning that as the temperature increased, the pressure also increased. So you can derive a similar expression to what we had for Charles's law. P1 over T1 equals P2 over T2. And you can see the graph here on the right side showing the direct relationship between pressure on my y-axis and temperature on my x-axis. Each of these lines is a straight line at a different volume. Okay, and so you can see how as the volume gets bigger from V1 to V2 to V3 to V4, the slope changes. Okay, they get closer and closer to the x-axis. Okay, and so you may have heard of Avogadro's law before, or Avogadro's number. Okay, Avogadro looked at what happens when there are changes in the amounts of substances. Okay, and so Avogadro figured out that if you have an open system where mass is allowed to go in or out, the volume is going to be directly proportional to the amount of gas that's present. Okay, and so here we're changing the amount, N, and the volume, V. Okay, and so we're going to keep constant temperature and pressure. Okay, so the way that we can write this is, because there's a direct relationship, V1 over N1 equals V2 over N2. Okay, and so this is one way to write Avogadro's law. In other words, if I allow mass to go in or out, but I keep the pressure and the temperature constant, the volume is going to adjust depending on how much stuff I have in here. Okay, so because you need certain conditions to hold, right, constant temperatures and constant pressures, it would be useful if you had a reference point for all of these things. And so we're going to call different reference points different names so that they're convenient. Okay, and so there's one that is called STP, which gets used pretty often. STP stands for standard temperature and pressure. So this has a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. So typically when you're working with gases or doing problems with gases, you're going to be using STP. Okay, there's another state that we'll see in Module 7 for thermodynamics called standard state. Standard state, the temperature is 25 degrees Celsius, and the pressure is 1 bar. So the pressure being 1 bar is almost exactly the same as the pressure being 1 atmosphere, but the big difference is the temperature. Okay, 0 degrees Celsius is very different from 25 degrees Celsius. So you have to be careful when you're doing these problems to make sure that you're doing things with the right state, whether it's standard state or STP. Okay, so now if you combine all of these relationships, it would seem that you can take all of these different equations, right? Boyles Law, Charles' Law, Galu Sack's Law, Avogadro's Law, and put them all into one equation. Okay, for example, they all have to do with volume, excuse me, except for Galu Sack's Law. So you would see that volume should be directly proportional to temperature, right? Volume is directly proportional to temperature. That was Charles. Volume should be directly proportional to number of moles. That was Avogadro. And the volume should be inversely proportional to the pressure. That was Boyle. So if I take all of these things together, I can combine them into one proportionality. Volume should be proportional to NT over P. And if I just rearrange this, I get that PV should be proportional to NT. And if I want to make this an equation, I can say that PV is equal to nRT. This is something called the ideal gas law, where R is something called the universal gas constant. And it makes the left-hand side basically equal to the right-hand side. Okay, and so this is a little bit of a preview of things to come of where the ideal gas law comes from based on these empirical observations.